Alright, so maybe we'll finish chapter 3, maybe we won't. You have the PowerPoint, you'll have the textbook, you can do it on your own. It's all pictures. Today, again, it's all familiar stuff, is descriptive statistics. You have already studied it. It's all familiar to you. So what I'll try to do is cruise real fast and real quick. You should know all of it by now. So there shouldn't be very many new things. In statistics, you deal with population and you deal with sample. Population includes everybody, and a sample is just a few. For example, the population for this whole class is supposedly 34 people, and we can just take these 9 people, and these 9 people will be a sample. You just need to know when you use samples and when you use populations. You need to understand basic statistical notations, such things as mu, which stands usually for mean, or pi, or whatever these are. This is basic statistics. And the observations are typically shown as x. The most common sign in statistics is a sum, so this is the summation sign. Nothing really interesting. You have number of measures. These are measures of location. Location tells you somehow how this is related relative to 0. For example, population mean. You guys are, I'm guessing, average age is about 19. Could be 19 and a half, could be 21, could be 20, but it's just about 20. So this population mean, you simply sum total everything, you divide by the number, and the population mean tells you you are about 20. Well, you can get the mean of your height, and maybe it's going to be 162, averaging out. You know, with the guys it may be 170, with the girls it may be 157, something like that. So it just tells you, and we're what, out of power? Huh? Is it a blackout? Well, it's a little trickier. Next one is a sample mean. Instead of taking the whole population mean, we can take only the sample. We just take let's say the average of these 7 or 9 people, and we're going to get what we can get from them. In other words, we look at these 9 people, and we would think that the average for the whole class will be about their average. In order for this to be true, these people need to be representative. They should look like the class, okay? Now, if we take a sample of these guys over here, would they be representative for the class? Do they look to you representative or not?
Yes.
Oh, to me they don't. They're all big, tall guys, mostly guys, okay? The class may be 50% girls and 50% guys, but the sample is going to have 80% guys, okay? So it is not representative in some ways, okay? There's some, okay? Now, they may be representative for GPA, okay? They may be just as random for GPA, but in terms of height, they're not representative. These guys are a lot taller than the average, because the average includes a lot of girls too, and they are a lot shorter. Okay, what else we got? Okay, next slide is, you can pull up your slides. You got those little toys like phones and stuff. You can pull up. I'm on slide number 5. When you pull up the slide, you'll see is we got an example 4.1, which we will do in the lab. Next is slide number 6. Another measure of location is the median. And the median basically is you order everybody according to height, or according to weight, or according to GPA, or according to income, according to some criteria, and the median will be someone right in the middle. So if you got 5 people, you're going to take number 3. If you got 3 people, you're going to take number 2. If you got 7 people, you're going to take number 4. Okay? So that's what the median is. And next slide, number 7, shows you a little chart with the median, which again we'll do in the lab next time. Another measure of location is the mode. And the mode gives you the largest number of people in a particular group. Maybe here the mode in the system for grades will be C, as most grades are C. Maybe the mode is B, okay? In terms of transportation, some use cars, some use motorcycles, some use taxis, some use tuk-tuk. Maybe the mode will be motorcycle, okay? So, the mode will tell you the largest number of whatever with certain characteristic within a population. Okay, it's coming back up online. Okay. And here is an example of a mode. You can basically run a histogram, and the histogram will tell you where you get most observations. Here the mode is 30 months, you can see over there. And here, the histogram, the highest. In other words, the mode tells you which is the highest bar in the distribution. You can also get the mid-range. And the mid-range, let's see if we got a picture. You take the minimum, you take the maximum, and the mid-range is just the middle between the minimum and the maximum. So it's a simple function of taking minimum plus maximum and divide by 2. So this is the minimum, this is the maximum, divide by 2. Fairly easy, fairly straightforward. Okay? And they just give you a basic example over here. Example 4 and 5. Again, we're going to try to do in the lab. Let's see what else we got here. Okay, well, here's a simple example. This is a distribution. You can see now, going back to the mode. The mode, you got a 12, whatever it is, days, and about 14 days. So these two represent the mode. You can also have what we did before, percentile. Percentile will tell you 90 percentile or 90% are completed within 3 weeks. In other words, 21 days will represent 90%. So percentiles are very helpful to tell you what percentage of the people are done below certain time, or have below certain income, or below certain GPA, whatever, again, the measure of interest is. Below certain weight, okay, below certain height. Okay. After the measure of location, the next one is dispersion. And dispersion just tells you degree of variation. We want to know how tall is the tall guy and how short is the short guy. Or we want to know somewhere in the middle. Maybe what's the difference between the 75% and the 25%? Well, range is exactly that, high and low. Interquartile range is, let's say, the 75% in the 25th%. So you order everyone. If you have 100 people, you take the difference between 25 and 75. You got variance, you got standard deviation. Range, the simplest measure, it's simply the difference between maximum and the minimum. Maximum and the minimum. You got a simple example. You take the highest number, you take the lowest number. You can ask Excel or SPSS given a maximum. Give me the minimum, and range is simply calculated maximum minus minimum. It's a simple number. Very easy to calculate. Here, the tallest guy is 180, let's say, and the shortest girl will be 150, and the range is 30 centimeters, okay? 150 to 180. Interquartile range, maybe 25th percentile will be for a guy, well, for everyone in class, not just guys, will be somebody tall 170. And maybe the 75th percent will be 160. So the difference between 160 and 170 will be 10 centimeters. So you take the first quartile and the third quartile. You take the 25th percent and the 75th percent. And you take the middle 50. Okay? And they give you a basic calculation on example 4.7. We'll try to do again in the lab. Now, if you know how to do these things, each of these takes less than a minute, okay? Maybe half a minute. If you don't know, it could take 20 minutes or 2 hours, right? Until you figure it out. And that's what the learning is about. Learning is about if something takes you an hour after you learn it to be able to do it in a minute. That's what it's about. Another measure will be variance. Variance is just a formula. It's given, it's calculated, and variances in statistics have some beautiful properties, okay? So, in example 4.8, you're given here, and you can see some and how the variance is calculated. We don't need to do that. There is a built-in function for what the variance, how the variance is calculated. What is important to understand is how you use the variance. And you use the variance usually by calculating from it the standard deviation. So the variance is just an intermediate step to get the standard deviation. And the standard deviation is the square root of the variance. And the standard deviation has some nice, good properties. Let's try and see what we have here. So, computing the standard deviation, they just give you what the formula is. You can use the formula, and here it is. These are some of the data. You can try to calculate the standard deviation or the variance for each. There is a Chebyshev's theorem, probably we don't want to study. Again, it's nice, it's beautiful, it's statistics. It gives you some properties. Maybe it's available, but we don't want to do that. And one of the most important things to understand is, are the empirical rules. And empirical rules are very simple. If you have object, come on guys. I think I gotta separate you. And the two in the back too, right? Yes, yeah, the two of you. Right, so the empirical rules are fairly straightforward. You can take a sigma. Sigma is the measure, just the number, the symbol for the standard deviation. If you take 1 sigma from the mean, in other words, you take plus sigma and minus sigma, which you do the other way. You take a minus sigma and a plus sigma, and it gives you 66% of the people or so. I think they give you here a different number, 68. I remember it as 66. Now, cameraman or woman, go over here. So, you got, this is your all, let's say the average here is 162. And let's say the standard deviation in this class is, let's say, 5 centimeters. So, when we take a sigma and a sigma, in this range here of minus sigma and plus sigma around the mean. This means from, and this is 5 centimeters and 5 centimeters, from 157 to 167 will include 68%. When you take 2 sigmas on the left and on the right, this means that you're going to be getting how many percent? How many? 95% of the people will be falling within this range. So 68% will be falling in the range of 157, 167. 95% will be falling in the range of 152, 172. That seems realistic for this class, okay? And then the last one will be 99%. Now it's almost everybody will be within 147 to 177. And probably on the low end it will include probably all girls, and on the high end we're probably missing 1 or 2 very tall guys, maybe guys like 180, maybe 182, whatever they are. Okay. Process capability index. How well? Okay, they got about manufacturing process. Maybe we'll see. It's not a very standard stuff. Again, you want to look at what's the mean and what's the mean plus or minus 3 standard deviations. It's a fairly straightforward calculation. You ask, tell me the mean. Computer tells you 499. Tell me the standard deviation is 0.11. Okay. Then you're asking, well, give me plus and minus 3 standard deviations. You know what it is. And then you're asking, are we getting, this is for quality control. Maybe we'll do it, maybe we will not do it. You can also get standardized values. And standardized values is somehow you try to normalize things. You normalize the variation or the standard error. You normalize it to the mean, and you use somehow percentages. For example, here 162 is the average, and let's say somebody is tall, I don't know, 170. So you do 170 minus 162, okay, and you divide by the mean, 162. And this gives you a number of about 8 divided by 162. And that's roughly what? That's roughly 0.05. About, okay? So basically, we say, it's kind of like 5%. You're about 5% above the mean, okay? It's very nice to use for income. The average salary, I'm just picking a random number, okay? Probably not representative in this classroom, but representative, let's say, for the city of Phnom Penh. The average income will be USD of $200 US. That will be the average, let's say, maybe 250, yeah?
I think it's divided by the standard deviation, not the mean.
By the standard deviation? Yeah, well, maybe, yeah. We have different measures. We can divide the difference, again, we can divide it by the mean, or we can divide it by the standard deviation. That's a very good option. So you can divide by the mean, that's true. And you get one type of z-score. Correct. You can instead normalize by dividing by the standard deviation. In other words, you can take x minus, let's say, xi minus x bar. X bar is the average, okay? And you can divide by the mean, and you will get one type of a measure. A completely different type of a measure, which is shown here, is you divide by the, is it sigma? Sigma or S, okay? Sigma or S, okay? So this gives you deviation over the mean. This gives you a deviation over the standard deviation, in other words. So if the mean here is 5 centimeters, okay, let's redo the calculation now. So you got 170 minus 162, and the standard deviation is 5 centimeters, okay. You would be getting about, what is it, 8 over 5. You're going to be getting 1.6. So you're 1.6 sigma higher, okay? So that's one way to think. Now, with the USD of 200, you can get a sigma of 50 probably will be representative. Maybe 20 will be representative for most incomes. In other words, 60% of incomes will be falling between 180 and $220. And now you may get somebody with $250, okay? So you can do 250 minus 200 divided by 200. So you're 50 over 200, that's 40%. So you're 40% above the mean. Or a different way to calculate is 250 minus 200 divided by the mean is 20, and this gives you 2.5 sigmas, 2.5 standard deviations higher, okay? All right, so you can use both. Here, in this particular case, they use the standard deviation. All right, so properties of z-scores, they got nice properties. Again, it's the same rule that we're using there, plus and minus 1 to plus 1 z-score gives you basically the 68% of observations. 2 z-scores, meaning minus 2 to plus 2, gives you 95. And then 3 z-scores, let's say from minus 3 to plus 3, will give you basically 99% of the observations. And they give you a simple example over here. You do your calculations, you do some standardized. We'll try to do the same thing on PSPP. It should be, I would think, very easy to calculate over there. There's an extra variable, z-score, and you just write in the formula, boom, calculates it for you. You can also get a coefficient of variation. In a coefficient of variation, you take the standard deviation and divide it by the mean. So here, we said that this particular person is 8 centimeters above the mean, so he's 5 centimeters above the mean. But we can also calculate what was the standard deviation. Sigma divided over the mean. The sigma is 5, and the mean is 162. So this equals to what? I don't know, 0.3. Okay, so the standard, well, it's actually how they call it here, the coefficient of variation will be 0.03, which is the same as 3%. Okay, so 3% difference will enclose again the same 68%, as long as the distribution is normal. Let's see what else we got. And you can apply the coefficient of variation. You got some stock prices. We'll try to get those. You got them for particular dates. You calculate the mean. You calculate the deviation or the standard deviation. And then the coefficient of variation. And hopefully you will be looking and checking into the reference manual. Maybe you already have the coefficient of variation built in. So you don't have to do the calculation, just say coefficient of variation of this particular variable, and it will calculate it for you directly. So some functions will be already given for you, you just write the function. And other functions may not be given, you have to calculate. You take the mean, you take this, and then you calculate it by simply dividing one to the other. It's actually going to be this divided by this. Okay, same thing, this divided by this. Oh, I got some here. Okay. Next one is skewness. And skewness tells you how uneven the distribution is. If you have too many on the left or too many on the right. Example will be, let's say, riches and rich people. You have a lot of poor people in this country, so a lot of them will be here. And then you're going to have a very, very, very few people who are very rich. Okay? And maybe the average would be, let's say, $500. And that will look realistic. But that's the average when you get the incomes of rich people who may be making $20,000, $30,000, $50,000 a month. But when you take most people, of what most people make, and most people will be making what we call the mode, okay? Most people will be making, I don't know, let's say between $200 and $250. Okay? So this will be representing the mode. This will be representing the mode. And this will be representing the mean. In other words, the distribution is not quite symmetric. We say the distribution is skewed. In this particular case, skewed to the left. So you want to know how skewed the distribution is. Well, this distribution here is relatively symmetric. I mean, you want to have a little bit here, but overall it's symmetric. Well, this distribution here is very asymmetric. It is very skewed to the left. Most of the observations are on the left. Now, if you take the United States, some distributions can be skewed to the right. The example will be, in America, you got too many fat people, okay? And very, very, very few skinny people. So, when you take the chart, and when you try to draw the skinny people, there won't be very many. And then you will be getting a lot of fat people. So, on the left side, you get very few skinny people, and on the right side, you get a lot of fat people, okay? Well, in a poor country like this, maybe it's the other way around. In a poor country where people are undernourished, you may get the opposite. You may be getting a lot of people who are relatively skinny, and then get very, very, very few fat people, for example. So, if people are mostly fat, it will be skewed to the right. If people are mostly skinny, it's going to be skewed to the left. A different way of thinking is, hey, most people here will be in the range of 40 to 55 kilograms. Most people here will be in the range of 120 to 150 kilograms, okay? So you can easily see on the picture. You can also say that here most people are skinny. You have a fat left tail. A fat tail doesn't mean that people are fat or anything to do. It means most people are on the left side. Here you got a fat right tail. Means most of the people are on the right side. A different way of saying is that the probability in a fat left tail is that the probability is higher somebody to be skinny. And in the right fat, the probability is that chances that somebody is more fat rather than skinny, okay? So, in this particular case, you got a fat left distribution, or fat left tail. And you got a simple measure, coefficient of skewness. It should be built in. You got a formula, you can write out the formula, or the statistical package will give you directly the formula. Examples again, you use the same one, and you got a certain example for what it is. Here is the coefficient of skewness is 1.66. So what we'll try to do in the lab is, again, pull the data, you already got it, ask for the coefficient of, in this case, skewness, and hopefully you get the 1.66. And for the other one, you get 0.60. Again, this will double check or verify that the work is correct by working through the examples. Another measure of distribution is kurtosis. Kurtosis tells you how peaked the distribution is or how flat the distribution is. If you get a very high peak, this means it's got a high kurtosis. Or the peak may be relatively low. So high peak means most people are bunching in here. Low peak means that it's very spread out. You got a lot of skinny people and you got a lot of fat people. High peak means most people are middle income. And then over time, you know, most people will get either rich or will get poor. In the United States, back in the 50s and 60s, distribution of income was very high-peaked, meaning that most people were middle class, okay? Well, the middle class is now thinning, meaning the middle class is going down, and now, I'll do this camera, try and zoom in, I'll redo the picture so you can actually see what's happening with America. It goes like this. Hey, the average is making maybe 30,000. I talked about 50 years ago. That's going to be more than 50,000 now, 60,000 now. So you will have a very few people with low income. You're going to have a lot of people around the middle class, and then you won't have very many rich people. That's the middle class here. Well, 30 or 50 years later in the United States, most of the middle class, like half the middle class is gone, okay? Most of these have become rich or poor. In America, most of them are poor. Most of the middle class has been impoverished. They've gotten into debt. They've spent their money. They bought toys that they don't need or want. So you will get a lot of people here moving, and some will have become rich. So the rich have gotten a whole lot richer. The poor have gotten a whole lot poorer. And most of the middle class have turned poor. Maybe of the middle class, 95% of the people who were middle class turned into poor. And then 5% of the middle class have moved to become rich. In other words, the tendency is for the middle class to get impoverished. Well, the trend here for the last, let's say, 10 or 15 years in Cambodia is the exact opposite. 15 years ago in Cambodia, there was little or almost no middle class, okay? You got a lot, well, sorry, a few very rich people, and I got a lot of poor people. Well, now the country slowly is building up a middle class. Maybe back then they were 1%. And every year you got maybe 2% or 3% added. So next year's going to be 4%. Next year's going to be 8%. So maybe by now, 15, I don't know, 10, maybe 15% of people here are already middle class. So here you got people moving out of poverty and slowly into the middle class. Okay. So here you have middle class getting created, and over there middle class is getting destroyed. All right, let's see what else we got. So that's a little bit about kurtosis. So in America, the kurtosis is basically going down, and here the peak is actually going up. You also have measures of location. Again, you could be, you see here, this is skewed to the left. A lot of observations are here. In other words, a lot of skinny people here, a lot of poor people here. This is a lot of fat people here, okay, on this side. And you can see how the mean, the median, and the mode will be changing. And let's cruise quickly. I think I can do the next 20 slides.
Is there a case where CK equals 3?
Again.
Is there a case where CK equals 3?
The CK, the coefficient of kurtosis is what?
3 equals 3.
3. Yes, of course. It can be 1, it can be 2, it can be 3, it can be 10, it can be 20. It is 3 when the distribution is normal. When the distribution is a nice, beautiful bell shape, it is symmetric, and it's normal. It's what we call kind of like perfect. But in the real world, most people's weight is not normal. In some countries, most people are skinny, and in other countries, most people are rich, okay? In some countries, you have very little middle class, so you're gonna have a lot of poor, like in the Philippines, and a few people extremely rich, like in Indonesia, okay? So, yes, you get 3, but that's rare, okay? Maybe you'll get 3 in the distribution of height in this class. You're all the same age, you're all somewhat representative, and your kurtosis, if we take your height, may likely be 3, okay? Let's see measures of location. This is what it is. Next one, Excel descriptive statistics. We're not going to use it for now. You can use the descriptive statistics. Okay, you can get some data. You'll get to look up. We're going to try to do the same thing and get the same data out of PSPP. Descriptive statistics for group data. We're not going to do group data. Probably not. They give you what it is and how it works, how many days and whatnot. Maybe we will, maybe we won't. Again, this is not as important to do right now. And what group data is. Group data, they grouped into cells. I will not do that. For example, group less than 10%, from 10 to 15, from 15 to 20%, from 20 to 25, from 20 to 20. And they tell what is the percentage, what is the numbers, what is the frequency, whatever that is. We're not going to do this. Let's see what else we got. Descriptive statistics for categorical data. Well, in categorical data, you want to know how many men, how many women, how many A's, how many B's, how many F's. So in categorical data, well, let's try. How many cars, how many motorcycles, how many taxis. Oh, how many come with a limousine, right? And a driver, maybe. So this is, well, if it's, let's say, categorical data in the movie theater. Right now, we got 5 movies running. Movie A, B, C, D, and E. Okay, you want to see how many people are going to movie A, how many people are going to movie B. Maybe that's what you want to know, right? Well, categorical data will be majoring in business, majoring in money and banking, majoring in, I don't know, architecture. Well, what's the percentage of business students, right? Okay, that's a simple question. You got some chart. We're not going to do this, these pivot tables, okay? They give you whatever the incomes are. Measures of association. We'll do some basic correlation. And covariance. Covariance tells you how close two variables track each other. Do they follow close to each other or not? Are they related or not related? And covariance is not standardized. So we want to use correlation. And correlation standardizes between -1 and 1. +1 means perfectly positive correlation. -1 will mean perfectly negative correlation. And 0 will mean basically no, or at least linear correlation. 0.1 or -0.1 will mean very, very, very weak correlation. 0.9 will mean very high correlation. Example here is we can try and get a correlation between your weight and your grades. Maybe if you're heavier, you'll have a higher grade. If you're skinnier, lower grade. Is that true or not true? Well, we don't know is the short answer. Maybe the heavier guys sit a lot and study a lot. Maybe the skinny ones just play around, have fun, and don't, I mean, we don't know. Maybe it's true, maybe it's false. We call this a hypothesis. It's a guess. But we can get the numbers for each student, run a, we call it correlation, and find out. Maybe there is none, maybe there is some. Maybe the relationship is opposite. Skinnier people might be doing better. I would think so, right? All right, let's see what else we got because we're done for now. You do the covariance. You see the picture shows you very nicely. There's a covariance and it's like positive. And here you see some pictures. Very nice positive correlation, very nice negative correlation. Pretty much no correlation. And you can do that, you will be importing the colleges and universities data set, and then you'll try to run some correlations from the software. And I think with this we're pretty much done. Okay, you got a correlation found. All right, that's good enough. Next time, see you in the lab.